Okay, so today we're going to be talking about the heat equation. We're going to be talking about the heat equation in every spatial dimension, and by the end of this video you should have a good idea of how to solve the heat equation in every spatial dimension and the origins of the heat equation. Because if you understand where the heat equation came from and you understand the derivation of certain terms, then you can pretty much solve it in any dimension with any coordinate system. Although I probably will make more parts of this video talking about polar coordinates. We won't be going over finite difference methods in this video. We're only going to be talking about exact solutions, so keep that in mind. So the heat equation may appear to be very complex, but it's actually quite a simple equation when you solve it. There are just a lot of parts to solving it. So I have a 5-point plan for solving the heat equation that I'll be going over in this video. And basically, before I talk about that, I want to talk about what you're actually trying to do. So what you're trying to do when you solve the heat equation is you're finding a solution to a differential equation, which means that you're finding a characteristic form that any equation can be in. So you're not actually finding a solution per se to every object or something. The bridge between the differential equation and the object is if you know an object, you know the boundaries of the object, and you know the heat distribution in the object, you can come up with a function, and then you can use a Fourier series to convert that function into a form that you can plug into the differential equation to find the time term. So in the first 4 steps in this video, we're going to be looking at just strictly how to solve the differential equation, the characteristic form that the equation must take, the function you have must take. And then in the 5th part, we're going to be talking about how to turn any function into a form that can be plugged into the differential equation. And the goal of this entire equation is to take some function of heat distribution and then find how it changes over time. If you're looking for the harmonic heat distribution, we're going to be talking about that slightly in this video. The equilibrium heat distribution, we're going to be talking about that slightly in this video. And it's going to come up in the form of the Laplace equation. So we're going to be talking about a little bit about how to solve the Laplace equation, but not very much. We're mostly going to be talking about it in this video because we're going to reference the steady state heat distribution. Okay, so here's roughly what our plan is going to look like. We're going to start by separating variables, and I'm going to talk about what that means a little bit later, but to suffice, it involves us breaking a partial differential equation into an ordinary differential equation, okay? So if you don't know already, it's very hard to solve a partial differential equation without breaking it into an ordinary differential equation, and there are a couple strategies to do that, so we're going to talk about separation of variables because it works in this case. The next thing we're going to do is we're going to find our characteristic solutions to the ordinary differential equations. We're going to wind up with multiple ordinary differential equations. We'll wind up with as many as there are variables in the equation. And the thing about the characteristic solutions is that we're also going to talk about where they come from, because when you get to things like polar coordinates, they're going to come back in the form that you can't really just use the characteristic solution to the Cartesian heat equation necessarily in polar coordinates. So we're going to talk about actually where they come from so you can come up with them yourself. Then we're going to talk about eigenvectors. And I'm calling them eigenvectors and not a constant. They're also referred to as a separation constant, but I'm calling them eigenvectors because the idea here is that when we have the ordinary differential equations, the system of ordinary differential equations, and we have them equal to some constant, because they're all equal to each other, the constant is actually an eigenvector because we have a linear system now, and we're trying to find one vector that they're all equal to, so that's an eigenvector. The next thing we're going to do is we're going to find a solution, which that's pretty simple. It just means we're plugging everything back in that we solved, all the ordinary differential equations, we're plugging them back into our coupling equation. And then the 5th step is not related to solving the differential equations. The 5th step is using a Fourier series to find the form that a function is in that's suitable to plug into the differential equation. The 6th step on here, the 6th step, wow, sorry about that. The 6th step on here is optional. It's basically talking about how to find the Fourier coefficients. It's relevant in higher dimensions. It's not a necessary step. It goes hand in hand with step 5. There are forms of the Fourier series that are in higher dimensions. You can find them, research them, but I just thought this was a good section to talk about because a lot of people don't understand where the Fourier coefficients come from, and it is important when you use a Fourier series in higher dimensions. Okay, so here's our heat equation in one dimension. We're going to start with the first dimension because it's a good building block for all the other dimensions, all right? So the first thing we're going to want to do is separation of variables like I was talking about earlier. So the concept behind separation of variables is that when you work with partial differential equations, the partial differential is only relating to the variable that you're working with. So because we have some function u, right, and u has multiple variables in it, the idea behind this is that if we assume that our solution can take the form of the function of a variable multiplied by the function of a variable, and you can do that with however many functions of variables you have, then you can break the system up, and because the partial is only relating to the variable that it's with respect to, you can pull all the other functions out front, as it were, and then separate them. So this works basically because when you think back to factoring just in basic algebra, you can factor out terms. You can factor out x's, you can factor out, things like that, variables. And so this is sort of the same concept. We're assuming that this function can be factored because we're assuming that it's a linear differential equation, which it is. So it's okay to make that assumption. It's okay to perform separation of variables because it is a linear differential equation. So the second line here is showing what that looks like. It's showing terms being separated out. And if you think about it, because we assume that u of x can be represented by, in this case, a function of x and multiplied by a function of t of time, we're assuming that that's all in the numerator because u's in the numerator. But the thing is, because the partial only relates to the variable we're working with, we're then pulling out the terms that aren't related to the partial, multiplying them on the front, and we're only keeping the term that the differential is related to in the numerator, and thus we render our ordinary differential equations. Okay, so the next part might be a little confusing, but just bear with me. So what we're doing here is essentially we're getting all the terms on each side, all the terms that relate to the differentials on each side of their respective differential. And this is just like in Calc 1 when you're solving an ordinary differential equation and you're getting all terms of x on one side, all terms of y on one side. But in this case, we're doing it with functions in their respective terms instead of just single variables and functions. So basically, what we're doing here is that because both of these differentials are equal to each other in the original form, because the partials are equal to each other, when we separate variables, we can assume that the terms are still equal to each other. The differentials are still equal to each other. We've simply separated them. And because, like I was saying, we treat anything that doesn't involve the partial differential as a constant, we can say, as far as it concerns one differential, the other differential with respect to the first one is just a constant. So they're both just constants to each other. So we wind up with these two ordinary differential equations that are equal to each other and thus both equal to a constant. And that's where our eigenvector comes in, because they're both equal to one constant. So essentially what we're going to do after this is we're going to look at the boundary conditions, and then we're going to find exactly what's going to constrain that constant. But for right now, in the third line of this, we're simply looking at the separation of functions onto their respective sides. So the final two lines, lines 4 and 5 on this page, are just the two ordinary differential equations that we're left with. And the first one's going to be easy to solve. The time-valued one is going to be easy to solve. The second one might not be so easy to solve, and we're going to talk about that in a minute. Okay, so now looking at the ordinary differential equation with respect to time. So I've kept this in terms of the function of time and the variable t. And there is no variable t in this actual equation, but I just want you to keep that in mind, because the function of t is just akin to y, and the variable of t is just akin to x. So I know this looks kind of daunting, but just keep in mind this is Calc 1, this is basic. All this is just an x and y kind of thing. I've just kept it in terms of function t and the variable t because I don't want it to get confusing. I don't want to call it x and y, or, like y prime and y or something like that. So, I've just kept it in this form, but the first line is just the entire equation equal to 0. So we're moving the eigenvector to one side in the second line, the eigenvector multiplied by alpha, and I never covered what alpha is. Alpha is just the convection coefficient, so it's like how fast heat flows through the actual thing. So we have the eigenvector times alpha times the function of time, and it's all equal to the first derivative of the function of time with respect to time, okay? So then line 3, what we're doing, we're getting the function of time on one side, so we're dividing out the function of time on the right hand side. We're getting 1 over the function of time on the left hand side. It winds up in the denominator. So the fourth line here, we have the derivative of the function of time over the function of time, and we're multiplying on the right hand side by the derivative with respect to time. Because the right-hand side is the side with the variable, the left-hand side is the side with the function. Again, this is just basic separation of variables, Calc 1. So now that we have all of our terms on their respective sides, I just rewrote this so it would be a little more clear. So we have the differential of the function of time on the left-hand side. This is the fifth line. The differential of the function of time multiplied by 1 over the function of time. And remember, what we're going to do next is we're going to integrate, so we want the differentials on each side. And we have it equal to the eigenvector multiplied by alpha times the derivative with respect to the variable. Okay, so when we integrate on both sides, these derivatives with respect to their components go away. And so we treat each one of these things, the function of t and the actual t, as their own variables. And so when we integrate this, we have 1 over the function of t, so that just becomes the natural log of the function of t, because we're treating the function of t like it's a variable. Remember, back to Calc 1. And then on the other side, because we just have two constants, the eigenvector and alpha are both just constants, and there is no actual variable t, we just add a variable t, because when you integrate anything that's a constant, you're adding whatever you're integrating for, you're multiplying by it. So we don't want this natural logarithm, we want that to go away, we want this just in terms of a function of t. So we're going to raise it to the power of e, so we do that on both sides, because e to the power of the natural logarithm of anything is just that thing. So then on the right hand side, we just have e to the power of the eigenvector multiplied by alpha multiplied by t. And this is just Calc 1, this is pretty easy, you can look up separation of variables if you don't understand this, but this is pretty simple and straightforward and to the point. So we're going to move on to the next equation now. I don't really think I have to talk about this one that much more, but if you have any questions, comment. So moving on to the next one now. Okay, so the second ordinary differential equation will not be as easy to solve. This is a second order differential equation, and whereas we can solve some second order differential equations with separation of variables, because this one does not have a first order differential equation inside, there's no suitable substitution we can make. So we can't do a u substitution, we can't do integration by parts, we don't render any meaningful solutions. So our next course of action is we can either use the characteristic equation or we can use a power series method for solving this. And we're going to use a power series method because later on when you solve the heat equation in polar coordinates, you're going to need to use Frobenius's method on Bessel functions. So a power series method is not only a way to get good intuition for how the characteristic equation works, but it's also good because it'll come back later in the form of Frobenius's method. Right, so whenever we use power series to solve a differential equation, we're going to start making the assumption that our power series is going to have two parts. It's going to have a constant and it's going to have some value related to x. Okay, so for the function of x, we're going to have the series from n equals 0 to infinity of some constant sub n multiplied by x to the nth. Okay, and then when we have our first derivative, we're going to pull the n down from the exponent in the x to the nth term, so we're going to multiply by n on the front, n times some constant that pertains to n multiplied by x to the n minus 1, because we're assuming that n is a constant, so we're subtracting 1. So then in our second order, we're pulling down n minus 1 to the front. We're multiplying by the original n that we pulled down in the first differential, so now in the second differential, we're multiplying n times n minus 1 times c of some constant times x to the n minus 2. And keep in mind that n doesn't actually change when we're taking the derivative. N is still just some number, so c to the n remains the same. Okay, so now we're going to sub our terms back into our original equation. You're going to notice that the first derivative is unused, so we're going to have the second derivative of our power series function. So we're going to have n equals 2 to infinity, n times n minus 1 times c sub n times x to the n minus 2 minus some eigenvector multiplied by the series from n equals 0 to infinity times c sub n times x to the n. And you'll notice that we run into a pretty immediate problem here, and that problem is that our series do not have the same base, okay? So we need to get our series in the form where they're the same base. Alright, so what we're going to do may seem complicated, but it's actually pretty simple. We're going to say that assuming that the second differential equation starts at n equals 2, we're going to sub in n plus 2. And the reason we do this is because if we think about it, if it starts at n equals 2, n plus 2 is 2, so if n is 0 plus 2, that's 2. So if we sub in n plus 2, we can start the equation at n equals 0 because it's the same thing as saying n equals 2 for where we start. So if we sub in n plus 2, we're going to get n plus 2 multiplied by n plus 1. And we're not going to, before we sub this in, you don't want to factor the n times the n minus 1. It just comes out a lot neater this way. You could factor it, but it wouldn't present as neatly when we try to find our recursive relation. So I'll talk about that in a minute. But we're going to sub in n plus 2 for n, and we get n plus 2 multiplied by sub in n plus 2 for n minus 1, we get times n plus 1. And now this is the important part. We're actually subbing in n plus 2 for c sub n, because keep in mind n doesn't change when you take the derivative, but n does change when you change the base of the series, because again, we're changing where the n value starts, which is why we're subbing in the n plus 2. So you get c sub n plus 2 multiplied by x to the n, and the n changes there too. It was n minus 2, but when you sub in n plus 2 minus 2, it's just n. And this is important, almost quintessential, because what we want to happen is we want to be able to factor out this x to the nth from our entire series, okay? So that's a really important part of it as well. Right, so step 3 is pretty simple. We're just factoring out the x to the n. Like I said, that's a pretty important part. You want to factor out the x to the n because it makes it easier to find our recursive formula based on n. We don't want any x components in our recursive formula. We want it to only be constants. Okay, so now it's all coming together. We're going to find our recursive formula for the constants, okay? So we have n plus 2 times n plus 1 times c sub n plus 2 minus the eigenvector multiplied by c sub 0 equals 0, okay? And if you think about it, if this whole thing needs to equal 0, right, and you have negative the eigenvector of c sub 0, then when you think about it, n plus 2 times n plus 1 times c sub n plus 2 must equal the eigenvector times c sub 0. Because if one is being subtracted from the other, they have to be equal, right? Okay, so the next thing we're going to do, we're just going to use some basic algebra. We're going to get c sub n plus 2 by itself, okay? So we're going to get c sub n plus 2 equals the eigenvector times c sub 0 over n plus 2 times n plus 1, okay? And we're going to keep it in this form. Like I said, we're not going to factor. It's a lot neater this way, I'm sorry. So if we keep it this way, the thing that you're going to be able to see is you're going to be able to see the factorials, because a lot of times in a recursive formula, you wind up with factorials. So it's good to keep things not in factored form. So step 5 is we're left with our relationship, our recursive relationship, and then we're going to find our recursive formula. Alright, so this is a pretty simple pattern, so I'm not going to talk about all these values. I'm going to talk about the first two though, because I think they're the most relevant. Alright, so let's say we plug in 0, so we get the eigenvector times c sub 0 over 2 times 1, this is just plugging in 0, and then we get c2 is equal to that, right? So then when we go down to c4, and I'll come back to when we plug in 1. When we go down to c4, okay, we plug in 2, so we get c4, because remember c is n plus 2, so when we plug in 2, c4 is equal to the eigenvector times c2 over 4 times 3, right? But we already know what c2 is, right? So if we go back to c2, think about it, c2 was the eigenvector times c sub 0 over 2 times 1, right? So what we actually get, therefore, c sub 4 is equal to the eigenvector squared times c sub 0 over 4 factorial. Alright, and remember, c sub 0 is just some number. Okay, so the pattern becomes pretty clear. Alright, when we have c sub 6, we have the eigenvector cubed times c sub 0 over 6 factorial. Okay, and so our pattern there is pretty clear. But let's go back to if we plug in 1. So if we plug in 1, we actually get the eigenvector times c sub 1. Which is odd, right? Because that's not c sub 0, that's c sub 1. So that's a different undetermined constant that we don't know. So we actually have two constants that we're working with here. Okay, and that makes sense. Normally when you have like second order differential equations and you use a recursive formula like this, you will wind up with two constants. But I just want to point out that's why they're in different colors. Okay, so blue is anything that deals with c sub 1, red is anything that deals with c sub 0. Again, the pattern's pretty clear. So for blue, our recursive pattern is that c sub 3 equals the eigenvector times c sub 1 over 3 factorial, and then c sub 5 is the eigenvector squared times c sub 1 over 5 factorial. Okay, so let's talk about the patterns now. Right, so the next thing we're going to talk about is the recursive formulas that we found. Okay, so we're multiplying by x to the n because we add both of these things together because there are two arbitrary constants. So both of these formulas we're going to add together because both of the arbitrary constants apply in the recursive relation, so we're multiplying them both by x to the n. Alright, so the one in red is the c sub 0 constant, so we get x to the n times c sub 2n, because remember, these are all the even values, okay? x to the c sub 2n is equal to x to the n multiplied by one fraction, which is the eigenvector to the half power of n, half power times n, multiplied by c sub 0 over n factorial. Therefore, and we're going to plug 2n in, so we get x to the n times c sub n is equal to x to the 2n multiplied by the eigenvector to the nth power over 2n factorial. And this should look familiar. This is akin to cosh of the square root of the eigenvector multiplied by x. And again, the eigenvector is to the half power over n factorial, and it's to the nth power over 2n factorial. So if it were to the power of 2n, there would be no square root, but it's technically to the 2n times 1/2. So it is to the square root power, or just to the half power, So now if we look at the c sub 1 value, we have x to the n multiplied by c sub 2n plus 1 equals x to the n times the eigenvector to the half power of n minus 1 times c sub 1 over n factorial. Therefore, again, we're just plugging in our c sub 2n plus 1. So we have x to the n c sub n equals x to the 2n plus 1 multiplied by the fraction, the eigenvector to the power of n multiplied by c sub 1 over 2n plus 1 factorial. And this isn't quite right yet. We're going to say that it's equal to sinh of the square root of the eigenvector times x, but only if c sub 1, which is an arbitrary constant, is equal to the square root of lambda. Now remember, c sub 0 and c sub 1 are just arbitrary constants, so they can be any real number. And because the square root of lambda is a real number, we can say that works. And if we assume that c sub 1 is any constant and not the square root of lambda, then we get this equation. We get c sub 0 times cosh of the square root of lambda multiplied by x plus c1 times 1 over the square root of lambda sinh of the square root of lambda times x. And again, c sub 1 and c sub 0 are just any arbitrary constants. So we can do that. We can make that assumption. That's the solution. C sub 1 and C sub 0, we can assume that they're any real value, and this will be a solution. So it's easier to write it this way. We want it in terms of cosh and sinh, because when we add them together, we get e to the something power, and that's really what we're looking for. So whatever's on the interior, when we add them together, we get e to the lambda, to the square root of lambda times x. And again, the arbitrary constants, if we make assumptions about them, we can clean up this equation a little bit. But any constant is going to be a solution because they're just whole numbers, they're not variables. So we can do that. We can make that assumption. Okay, so now we get into one of the most important points that we're going to make with power series, alright? And remember how I was talking about how c sub 0 and c sub 1 are just arbitrary constants, alright? So when you use Euler's formula, you may be thinking, okay, well, what if we have something to the imaginary power, right? Like, let's say we have e to the imaginary power times x. We're going to wind up with cosine of x plus I times sine of x. And you might be thinking, well, you know, in our characteristic equation, they say, and I'm getting a little ahead of myself, but they say that a characteristic solution of this is just cosine of some eigenvector times x plus sine of some eigenvector times x, and there's no imaginary power. But see, e to the imaginary power times x, which is e to the square root of negative lambda, think about it, because the square root of any negative value is going to be an imaginary number or a complex number. Think about it, that's going to be a problem now, because we're thinking like there's this I term in Euler's formula, but it's not showing up, right? So this slide is all about talking about what happens if lambda is negative, right? Like, what happens if it's negative? Because the thing here is, when we have this negative lambda term, what we see actually is, because when you go through this series and lambda is being multiplied each time and it starts off negative, it alternates from negative to positive, right? So this cosine series stays cosine, right? But this sine series only works under the assumption that it's the square root of lambda. And you might be thinking it's the square root of negative lambda, right? Because when you do this, you might be thinking, well, okay, there's this, you know, negative lambda term, right? I want to multiply by something that has I in it, because I've demonstrated down here at the bottom of the page, when you have, you know, x times the square root of negative lambda, then you're essentially getting negative lambda to the half power, right? And you're getting some imaginary number, but it follows our recursive relation, because then on the next one you get x times, lambda to some increment 1 plus the half power, and then you get plus, 2 plus the half power, right? And you continue like that, and you always go up by an increment of a half power, which is what you want if you're multiplying by the square root of something. But the thing is, it's actually not going to be the square root of negative lambda. C1 is actually going to be a real number. It's actually going to be the square root of positive lambda. Because, and this is important, because according to Euler's formula, there's already an I term. Okay? So actually, here's the brilliance of it all, right? So we have e to the ix equals cosine x plus I sine x, right? And we get that that's equal to cosh of ix plus sinh of ix, right? So when the terms become sine and cosine, the imaginary parts go away. They're factored out, right? And the thing is now, the formulas are the same. The recursive formulas are the same, right? So now, due to Euler's formula, we know that sine is I sine of x, right? And we know that according to our last formula involving sinh, if it's negative, it's just going to be sine, but there's this I on front. So we have c sub 1 over the square root of negative lambda, right? But because there's this I on front, it's multiplying the numerator. C sub 1 is actually just the square root of lambda, right? So we can factor that out entirely. So here's the cool thing. Sine of x, lambda is just going to be the square root of positive lambda. I'm sorry, c sub 1 is just going to be the square root of positive lambda, because we factored out that imaginary part entirely, because we can assume that c sub 1 is an arbitrary constant, and c sub 1 in our recursive formula doesn't involve I. So it can be factored into the terms. We can factor out the imaginary part entirely. It's just the square root of lambda. The terms alternate, and thus we can factor out the imaginary part entirely in the series. Okay, so now we're left with sine and cosine, just sine and cosine. So that's really beautiful, and that's one of the reasons why I wanted to do the power series, to demonstrate that because c sub 1 can be any arbitrary constant, we can factor it out. The arbitrary constant is actually the square root of lambda, and that gets us our formula. So great. So now that we have our characteristic solutions, we no longer need to do the power series solution every single time. You have to be certifiably insane to do the power series solution every single time. There's no reason for that. We have our characteristic solutions. So basically what we're going to do here is, because we want lambda to either be entirely positive or entirely negative, just as a formality, we're going to call it lambda squared. And when it's negative, we're going to call it negative lambda squared, because that ensures that all the values are either going to be positive or negative, right? So when we have lambda squared, the solution, the square goes away, by the way, because again, if you recall in our characteristic solutions, the exponent was the square root of lambda, so when it's squared, it just goes away. Negative lambda is just positive lambda, but without the sinh term. It has the cosine and sine terms. Without the sinh and cosh terms, I'm sorry. So anyway, the negative part goes away. So we're left with either lambda squared, which is all positive, equals e to the lambda x plus e to the negative lambda x. And then we have our negative lambda squared is equal to cosine of lambda x plus sine of lambda x, okay? So the idea here is we have characteristic solutions, and any of these work, and that's fine or whatever, but like, we're going to go farther than this, because again, we're solving the equation, so we want to find a meaningful eigenvector, alright? Because, as it turns out, based on our boundary conditions, not all of our eigenvectors are meaningful, okay? And so we really want to assign a value to that lambda. We don't want to leave that lambda, because that lambda is not an integration constant, it's not an arbitrary constant, it's an eigenvector. It's something that both of these equations have to be equal to. So we're going to look at the boundary conditions now, okay? So let's look at the boundary conditions, right? So we want our function in our spatial direction. We want our function of x at 0 when x is equal to 0. We want the y term, or the function of x of 0, to be 0. Okay, and then we want when x is equal to some length. So the length can be anything. So we're going to assign a value L. We're going to say when the function is at a certain length, it's equal to 0. Okay. And the reason we do that is those are like our fixed points, right? Those are like our homogeneous boundary conditions, okay? And those are our Dirichlet boundary conditions, all right? We also have Newman boundary conditions. This is sort of important to note. We don't care about them right now because the Newman boundary conditions actually arise from something called Fick's law. So we don't care about them right now. Basically what they are is they're saying the derivative at the boundaries is also equal to 0. And we do this because, let's say it's not equal to 0, one of two things are going to happen. We're either going to assume that there's a cusp point or not a discontinuity, but a point where the function is not differentiable, and that provides a weird circumstance for our boundary, and it's also not the way heat behaves. And then also, let's say the function is continuous and differentiable. That means that the function is still sloping at the boundary, and therefore the boundary is not meaningful. Therefore, you're not solving for the heat correctly. There's some heat change on the other side that you're not anticipating. So we don't want to do that. We just want the slope at the boundary to be steady, but we're not actually going to solve using the Newman boundary conditions, because the Newman boundary conditions, like I said, what we're trying to do with this is you're given some heat distribution initially. So whatever equation you're given, the heat should be a normal distribution, you know? So I'll talk about examples of when you can solve something that doesn't have Newman boundary conditions, and you can still do that. It's just not going to provide a real-world solution. It's not going to provide like a meaningful solution to the heat equation. So we just want those to be the way that they are. But to actually find the eigenvectors, we're going to use the Dirichlet conditions, okay? So the Dirichlet conditions are like the most important thing to us right now. We're going to use them to ascertain our eigenvectors. Right, so the first example, the first eigenvector we're trying to solve for is if the eigenvector is equal to 0. So we're pretty sure that this isn't a solution, because if the boundary conditions are homogeneous, you know, why would it be? Because if the second derivative is equal to 0, the shortest distance between 2 points is a line. If the points are homogeneous, the boundary points, you know, the line intuitively should just be a line. That should be the only solution. But we'll solve this out just to prove it. So, you know, again, if the second derivative has to be 0, then there's no way that we can have x to the power of anything over 1. So we need to have a y equals mx plus b equation here. So if we assume that, you know, at a certain, if we assume that at the initial condition, you know, if x is 0, it's always good to start with 0 first, not L. It's always good to start with the zeros first. If we assume that x equals L at some point, then we have this b value left over. So we have to assume that b is 0, because according to the boundary conditions, you know, the initial point is 0. There's some initial point that's 0, and the initial point should be, you know, 0. It should be x is 0, y is 0. That should be our starting point for the homogeneous boundary. So, you know, if that's true, then b has to also be 0, right? You can't be adding something there. So again, and we'll talk about if the boundary conditions aren't homogeneous, because you can solve for that, but it involves using Laplace's equation. We'll talk about that later in this video. But for right now, we're going to assume that the boundaries have to be homogeneous, and they have to be 0 at least 2 points in the 1D case. So, you know, if we assume that b is now 0, then according to the L condition, L times x has to be equal to 0. I'm sorry, L times m has to be equal to 0. What is wrong with me today? Sorry, L times m has to be equal to 0. So basically what that means is, because L is some number that isn't 0, x has to be 0. So again, this is just a straight line. There's no meaningful eigenvector value here. So m and b are just constants. There's no eigenvector even in this equation, so we're just looking at constants in this case, and the constants don't even hold up. So I mean, this is like, this solution we're totally discrediting. 0 is rarely, if ever, a solution. So we're going to move on to our positive eigenvectors and our negative eigenvectors, not our 0 eigenvectors, okay? So we're going to move on to that now. Okay, so let's look at the positive eigenvector first, okay? So and by positive eigenvector, I mean positive in the power series solution. In reality, this is actually talking about if the eigenvector initially is negative, all right? So if we look at the positive eigenvector in our power series solution, we're going to say that for our initial condition, we're going to plug in 0. We're going to get c sub 1 times e to the 0 plus c sub 2 times e to the 0. We want this entire thing to be equal to 0. So basically, because e to the 0 is just 1, we get c sub 1 plus c sub 2 equals 0. So c sub 1 equals negative c sub 2. All right. If we plug that back in, we get c sub 1 e to the lambda L minus c sub 2 times e to the negative lambda L, and again we're plugging in L for x. So we actually, there is a point here when c sub 1 and c sub 2 can be anything in the equation will still equal 0, but that's only at 0. That's only when x is equal to 0, and again, L is something other than 0. It has to be something other than 0, so this is not meaningful. Everywhere else on the graph, the graph will not touch 0 if x is anything other than 0 in this situation. So, like, we don't even need to prove this logically. We just know that graphically this is not going to touch at any other point than 0, okay? So now we're going to move on to what is initially our positive eigenvector, but in our power series solution it's negative. This is a little confusing to think about it. Just think of it like in our initial differential equation. If we had the second derivative plus the eigenvector times the function, it's actually going to be the negative eigenvector, okay? According to our power series, and you can go back to check that that's true. So here we have c sub 1 times cosine lambda x plus c sub 2 times sine lambda x. So we plug in 0 again, always great to start with 0. In this case, we actually eliminate a term. This is a great example of why you start with 0. So we have c sub 1 times cosine 0, which is times 1 because cosine at 0 is 1, plus c sub 2 times sine of 0, which is 0. So we're left with c sub 1 equals 0. So c sub 1 has to be 0, right? So now we just have c sub 2 sine lambda times L, right? And again, we eliminated a whole term here, so that's great. So now we have that lambda L in sine. We have to have sine equal to 0 for c sub 2 to be any constant. C sub 2 can be any constant when sine is equal to 0. So when is sine equal to 0? Well, we know sine is equal to 0 at any increment of pi. We know that n is a whole number increment in a series. We know that n pi, sine is equal to 0 at any increment of n pi. So we know that lambda times L has to be equal to n pi. Doing some simple algebra, we know n pi over L has to equal lambda. So that means when we have our x term in here, when the eigenvector is n pi over L, and x in the numerator is the length, we know that 1 over the length will get us some term n pi, and then that's going to equal c sub 2. I'm sorry, that's going to equal 0, and then 0 times c sub 2. C sub 2 can be anything. Therefore, this is a meaningful solution. Therefore, we're going to stick with a negative eigenvector in terms of our series, aka a positive one initially, meaning that our initial equation should be the second derivative plus some eigenvector times the function is equal to 0, and that means that we're going to have some heat equation that has c sub 2 sine n pi over L times x in it, and that's our solution. That's our meaningful solution. So now moving on. Oh, and before we move on, just to clarify, another way of thinking about this, when lambda is negative initially, when we have the second derivative plus some function, I'm sorry, the second derivative times 1 over some function is equal to negative lambda, and then we multiply by the function on the side, we get the second derivative is equal to negative lambda times the function, and then we add lambda, and then we get the second derivative plus lambda times some function, basically, and that's equal to 0. Basically what we're saying there is that when lambda is negative, the rate is negative, okay? Which means that the heat is decreasing over time, which is what we want. I'm sorry if that was unclear the way that I phrased that, but what I'm trying to say is that lambda has to be negative because we know that the heat is decreasing over time. So that's the only relevant solution. The heat equation is only relevant when heat's decreasing over time. Heat doesn't increase over time if it's greater or less than the boundary conditions. It has to decrease. It has to approach the boundary conditions. So lambda has to be negative. Sorry if I didn't clarify that when I was saying that the series had to be negative, the initial had to be positive. So, sorry about that. So that's what I meant. Right, so now we have solved our entire heat equation in 1D for our characteristic solution, okay? So we have u of x and t is equal to some series from n equals 0 to infinity of c sub 2, which is just a constant, times sine of n pi x over L multiplied by e to the power of negative alpha multiplied by n pi over L squared times t, okay? And so, again, we have simply plugged in our eigenvector for our initial solution to that equation a while back, that equation of E that we did. And again, our eigenvector is negative, keep this in mind, remember our eigenvector is actually negative. It only becomes positive when we plug it into the sine term. Because again, the eigenvector starts off negative initially, and then when we plug it into the sine term, it becomes positive because of our characteristic solution. So in the e term, it will be negative. So we have our entire solution now, and that's great. So now we need to make any equation conform to that solution if it has the correct boundary conditions, and what we're going to use to do that is the Fourier series, alright? So below I've written the standard Fourier series formula, okay? And this is for a Fourier series involving x and y, so basically a Fourier series in one dimension. And again, this isn't going to hold up in higher dimensions, because again, the heat equation, it's not like we just want to do it in 1D, we want to do it in 3D. So we're going to talk about the Fourier series now, because now we want to talk about how it was derived, so we can convert any function into an acceptable form, and we can do that in any dimension, alright? So we're going to talk about the Fourier series now. So another important thing to keep in mind about the one-dimensional Fourier series is that we actually have three coefficients. We have c sub 0, c sub 1, and c sub 2. And c sub 0 is not relevant because it only comes up in functions of two parts, or periodic functions, such as square waves or sawtooth waves or something like that. And what it is when there's a jump discontinuity, it's basically the halfway point. So c sub 0 is not going to be relevant in this problem. And for the sake of our equation, we're going to assume that the only relevant solutions we're going to find are in the form of B sine series. So we're actually not going to worry about the c sub 1 term right now. We're only going to worry about the c sub 2 term right now. One of the most interesting things about finding the Fourier coefficients is that we're actually finding them using concepts from vector calculus. We're actually not finding them using algebraic ideas. We're using ideas from vector calculus. So actually what we're going to do is we're going to use orthogonal functions to find our Fourier coefficients. So there's a couple identities that you have to remember, and we're going to prove those a little bit later, but the first identity that you're going to remember is that when you have the integral of two sinusoid terms multiplied by each other that have n pi in their brackets, the solution is going to come out to be 1 when n is equal in both the sinusoids, and the solution is going to come out to be 0 when n is not equal in both the sinusoids. And the other identity we have to remember is that we have the integral of two dissimilar sinusoids that have n pi in their brackets. It's always going to be 0. Alright, so we're going to prove both of these things because that's going to help us find the Fourier coefficients. And just to give you a visual idea of what I'm talking about before we even go about proving this, when we have the Fourier series, right, we know the function of x is equal to the series from n equals 1 to infinity c sub 1 cosine n pi x over L plus c sub 2 sine n pi x over L, right? So the thing here is, because the function of x is equal to these things, right? The function of x, when we integrate from L to negative L, and then we multiply by sine n pi x over L by the function of x on one side, on the other side, what's actually happening is we're integrating and multiplying these terms, these sinusoid terms, and if we multiply by sine, you'll notice the cosine term will be 0, so the c sub 1 coefficient will go away, even if the c sub 1 coefficient isn't necessarily 0 in the problem, but for the particular coefficient we're trying to find, c sub 1 will go away, so we'll be left with c sub 2 when the sinusoids are the same, and so we get c sub 2 is multiplied by 1 when n is equal, which it is in this case in the series. I can't think of an example where it wouldn't be equal in this kind of a series. I just listed that identity to clarify that, but in this case n is equal, so c sub 2, because we're multiplying by similar sinusoids when we're finding c sub 2, because f of x is equal to the Fourier series, the integral from L to negative L of the function of x multiplied by sine n pi x over L, is approximately equal to c sub 2. And again, there is one more step that we have to take, so we're going to prove this on the next page with integrals. The last step we're going to have to take is by multiplying that entire integral by 1 over L. And so it's easier for me to just prove why this is true on the next page, so I'll talk about that in a second. Right, so the first identity that we're going to prove is when the sinusoids are equal, and we're going to be looking at the B sine series, when the sinusoids are equal and the n term is equal, alright? And so those are the two assumptions we're going to make going in. So you might be confused as to what's happening on this page. So what we're doing is, first of all, we're making an Euler substitution because it's just a lot easier. I know that some people swear by like trig identities when doing integrals, but I really hate doing that, and I think that there's no point to it. And I think if you can do an Euler substitution, you should absolutely do that. It makes the integral a million times easier. So the first thing we're going to do is we're going to assume that based on our exponents, sine is going to be equal to sine of n pi x over L is going to be equal to e to the I times n pi x over L minus e to the negative I n pi x over L over 2i, and all of that's going to be squared. Okay, so this is just basic algebra. We're factoring out the top. The bottom obviously becomes -4, so the top is going to become e to the 2i n pi x over L plus e to the negative 2i n pi x over L minus 2, and you can check the math on this if you want. We're just, I've written it on the top, you're simply factoring the e terms, so that's not that hard. So now the next step, we're going to pull the -1/4 out to the front. It just makes things easier. So now we're left with the integral from L to negative L of these terms. Some people, when they do this, they like to simplify. They like to say multiply by 2, and it's from L to 0, because L and negative L, the series is symmetrical, but you can do it either way. So we're going to make a u substitution. We're going to say that u is equal to 2i n pi x over L. We're going to say that du is equal to 2i n pi over L. And so what we're going to do here is we're basically going to say that our dx value is 1 over 2i n pi x over L. Okay, so it's going to apply to all the e terms. All right, so when we have -1/4 and then we take the integral, we're going to have -1/4 1 over 2i n pi over L for all the e terms, and then -2. -2 is just a constant. There's no u term in there, so we're not going to do a u sub for 2. We're just going to tack on x because that's what we are integrating by, so it's going to become -2x. All right, so the e terms, what's going to end up happening here is we get 1 over n pi L on the front, and what ends up happening is because there's a 2i in the denominator there, we're going to keep the e terms together. We're not going to distribute the 1 over 2i n pi over L. We're just going to have 1 over n pi over L on the front, and we're going to distribute the 2i but nothing else. And when we distribute the 2i, you'll notice that these e terms look very similar to our original sine series. So when we have 1 over 2i and we distribute it, this entire thing is just going to become sine n pi x over L multiplied by 2, and you can see that. You can see the e and the minus e to the minus something power, and then so you just look at the powers are the same, so that 2 on the front is just going to multiply the n pi x over L, so it's just going to become sine n pi x over L times 2, and remember our bounds of integration, we're looking at L and negative L, so the sine term is going to equal 0, right? So because even if it's negative L, the sine term is going to be 0. So it doesn't matter. If you pull out L and you say 0 to L and you pull a 2 out on the front, or if you choose to integrate for L and negative L, it's going to be the same thing. I chose to pull out the 2 just because it's a little bit easier. So the next thing we're going to do is just pull out the 2. We're going to say from L to 0, or 0 to L, I'm sorry. And we're going to say instead of -1/4, it's -1/2. We know that this entire term is irrelevant when we plug in L. We know that the entire sine term is going to be 0, even if we're multiplying by 2. It doesn't matter because it's an even value of n pi. So it doesn't matter if we're multiplying by 2. 2 times n pi in a sine term is still going to be 0. Sine of any whole number of n pi is just going to be 0. And so the 1 over n pi over L on the front, that doesn't matter. So then we're just left with -2, and we're left with -2L, right, because we plug in the L now. So now we have -1/2 times -2L, our entire integral's done, and we're just left with L now. So now that we're left with L, that's where our 1 over L term on the front comes from, because there's an L inside here. Remember, our orthogonality only applies assuming that there's a constant of 1 multiplied by n pi in our original orthogonal terms. So actually when we have L in here, when we prove it with the integral, we're going to prove that we're actually left with n pi times whatever L is. And so whatever L is going to be, we're going to put a 1 over L on the front, and then the term will just equal 1 in our orthogonal series, and we'll be left with the b sub n term. Right, so now this is just going to be a quick proof. I don't need to do the whole integral of this, but this is going to be a quick proof of the dissimilar sinusoids, because remember, we still have that cosine term. We want to get rid of it because we don't know what C sub 1 is. C sub 1 is irrelevant. I already said that. We're working with B sine series, but just to prove this in case C sub 1 isn't irrelevant, we're trying to find the Fourier coefficient of just the B sub n, or C sub 2 sine series. We're going to say that basically what we're going to do here, it's the same thing. We're going to make an Euler substitution. So we're just going to have the identities of sine and cosine. And it doesn't really matter what's in the denominator, but just take a look at the numerator. We don't have a constant term in the numerator. So I chose to do the other series first because remember that constant term was the only thing that ended up mattering, right? When we integrate this now, we're going to end up with, we're just going to end up with something that there is no constant on the end, and it's some variation of n pi, and you have L on the interior. So this entire thing is going to be 0. It doesn't matter what the coefficient is. Because we have no constant term being added, we don't even need to integrate. We can already tell this is going to be 0. And if you want a more intuitive proof of this, you can just, it doesn't matter what n is, as long as n's a whole number, you can graph this and you can see that actually for sine times cosine or a dissimilar sinusoid, it's actually going to be a graph that is this, how do I phrase this? The graph is positive on one side, negative on the other side, and it's symmetrical over the axis. So on one side it's negative and it's equally positive on the other side. So therefore the integral is going to come out to be 0 because the positive and negative just cancels. Whereas with the similar sinusoids, you get a symmetrical series that's completely symmetrical on both sides, and it's 2 times that thing. So here what's happening intuitively is that we're not going to wind up with a constant term, and our entire integral is just going to be 0 for some length of L. Because remember, if L is 0, if L ends up equaling 1 in the sinusoid, I'm sorry, not if L is 0, if L ends up equaling 1 in the sinusoid, it's multiplying by some n pi, and then that entire term is going to be 0. So it doesn't matter how we integrate, it doesn't matter what the coefficient is, there's no constant term on here, so we know that those e values, they're going to, when we finish integrating, they're going to turn back into some form of sinusoid with maybe some value on the interior, maybe some coefficient on the outside, but there's no constant. So this entire term is just going to be 0. We proved that with our last example, that the constant was the only thing that mattered. Right, so now we have our entire one-dimensional heat equation. That's all done. So now we know what to plug in for the constant. We have our entire solution has a function of x in there, right? So now we can take any function of x and plug it in and get a solution to our heat equation, because now we know the coefficient. So we're done with the one-dimensional example. Now we're going to move on to the two-dimensional example. We're going to talk about the coupling equation, and we're going to talk about finding those orthogonal vectors again. And then once we do that, you should have a good grasp on all the concepts. We'll move on to the three-dimensional case, and I'll talk about exactly what that'll look like in 3 dimensions. So let's talk about the two-dimensional case next. Before we go on to the two-dimensional heat equation, there's something important that I do want to mention. I want to mention what happens when the boundary conditions are non-homogeneous. Before I mention those Dirichlet boundary conditions and those Newman boundary conditions, and the thing here is that if the Newman conditions apply, alright, and I'm saying only if the Newman conditions apply, if we have some function where the Newman conditions apply but the boundary conditions are not necessarily at 0, what we will do is we will use the Laplace equation to find our steady state portion of the heat equation. And the thing is, with the heat equation in any dimension, you're simply taking your variable portion and you're adding your steady state portion. And you might think, like, well, that's really simple, how does that work? And the idea behind this is that when we add our steady state portion, it's deforming the plane of the graph, so that when we have our heat equation, our variable portion, we're treating the boundary conditions now when we're solving as that they're 0. And that when the boundary conditions vary and we find our steady state portion is going to deform the graph by a certain amount. So I have here a graph sort of attached to help you visualize what that means. And so basically what's going on here is that when we have some graph that's shaped like a bell curve, and we have some function, in this case it's just y equals x. If we add it to our bell curve function, the bell curve will be deformed by that function, because every y point that we get now for that x value is going to deform the function by that amount. So the bell curve will conform to the new line, and that line will essentially be like our steady state. And so when we take the derivative of that line per se, like if we were doing this with the heat equation, that line would conform to the steady state and not to the just like a flat line or a flat plane or whatever, if the boundary conditions were 0. So all you have to do when the boundary conditions aren't 0 is you simply add the steady state portion, and then you treat the ensuing heat equation like the boundary conditions are 0, because when you solve for the variable portion and you have that steady state portion, your graph, as it were, is going to conform to just whatever the steady state is, whatever you add. So because the Laplace equation, the idea behind the Laplace equation is that when you have all the partials equal to 0, that means the second derivative of your function is equal to 0. That's the shortest possible distance for all the partials. And again, because these are partials, because they're not just straight derivatives, we're not going to wind up with just a completely flat surface. We're going to wind up with basically the optimal coverage of a surface. So the surface could still be curved in 2 or 3 dimensions, but essentially it's the shortest possible distance that the curve has to be. It's the optimized covering of that thing. So it's our harmonic heat distribution. It's when the heat distribution hits 0. Essentially, it's when the heat distribution conforms to the boundaries exactly. So that's where our Laplace equation relates, and again, that's how we take our steady state. We simply add that to the problem in whatever dimension. We take the Laplace equation in whatever dimension we're working with of the boundaries, and then we simply add it to that problem. Okay, so I'm just going to brush through this quickly. This is the solution in 2 dimensions. Again, this is just the separation of variables part of it. You'll notice that there are these 2 symbols, which I've represented with Jupiter and Saturn. This is our coupling equation. And this may look complicated, but the idea behind the coupling equation is that when we have the time derivative equal to the 2 spatial derivatives being added together, and we know that these 2 spatial derivatives are both equal to 2 different constants, then we know, because they're equal to 2 different constants, we know that the time derivative is equal to those 2 different constants added together, because it's equal to the 2 other spatial derivatives added together. So the idea of the coupling equation is pretty simple to understand. It's just, again, we're just having the constants, instead of 1 eigenvector now we have 2, and because the time portion of the equation isn't constrained, it's only our spatial portions that are constrained. Our 2 different eigenvectors are going to be solved for, and then we're going to end up just adding them together, and that's going to be the time eigenvector. So, and again, the spatial dimensions are not really related to each other, so we can just add those together, because the spatial dimensions, their eigenvectors aren't really constrained by one another. They're just constants to each other. So the coupling equation, that's the idea. The time differential equation is just equal to the 2 spatial derivatives, and therefore it's equal to the addition of the 2 spatial eigenvectors. And it'll work the same way in 3 dimensions. So that's all a coupling equation is. Okay, so now we have our entire 2-dimensional heat equation minus the Fourier coefficients, right? But we know how to derive those because we talked about it earlier, all right? So keep in mind here, we actually have 2 series terms, all right? And that's not because in our 2 series we have n and we have m, and that's not because n and m are not the same thing. They can be the same thing. However, we keep it as 2 series just to clarify that the series apply to 2 different variables, okay? Just like how integrals apply to 2 different variables, the series apply to 2 different variables, all right? And in that same vein here, we're going to say that when we find the Fourier coefficients here, because the integral only pertains to 1 variable, our orthogonality does not apply to the other term, whether the sinusoid is similar or dissimilar, okay? So what we're going to do now is we're going to have the series from m equals 1 to infinity of sine m pi y over w, okay? We're going to have 1 over w times the integral from w to negative w of the function of xy times sine m pi y over w equals some constant, right? And because we're deriving that constant, we're keeping it by itself. Because the integral only pertains to dy, we're treating everything with a term of x as a constant, right? This is just simple integration. This is Calc 2 or Calc 3, right? So now, because we know that c is equal to the interior series, because the interior series applies to a function of x instead of a function of y. It's a different spatial variable. Again, functions of x and y now, these are directions. These are not y equals x functions. These are directional functions, okay? So now, looking at our function of x, we're now going to institute a double integral. We're going to do the same thing, okay? So on the same side, we're going to do 1 over L times 1 over W times the integral from L to negative L. And then we have the integral of w from negative to w. We already had that of the function xy sine n pi y over w. And then we're going to multiply that by sine n pi x over L. And that's all equal to c sub surface, c sub s. And I've denoted it c sub surface because what we did is, because we had two sinusoids and we knew that they both had their constants c sub x and c sub y, and they were multiplying by each other, we simplified it to one constant. We said c sub xy, and we denoted it c sub s as a surface, okay? And so, again, the idea behind this entire thing is that because the Fourier series, because our solution to our heat equation we've proven is essentially a Fourier series, this double Fourier series, because it has two series terms, this double Fourier series, the orthogonality only applies to the term with the respective variable. So when we take a double integral, because each integral refers to a different respective term, we can treat the interior product as a constant, and then we can find the orthogonality of that constant after we do the first integral. So that's where the second integral comes in. So the order of the series does dictate the order that you take the integrals in, but the order of the series in terms of this heat equation actually doesn't really matter in this particular scenario. But do keep that in mind, that the series terms do matter in some situations when you take the orthogonality, when you find the vector products that get you those orthogonal identities. So now that we've done that, now that we have the orthogonal equation here, the double integral, because it is a double integral because we're taking it in two dimensions, we understand how to derive the Fourier coefficients for any dimension now, basically. So now what we're going to do is we're going to have the two-dimensional equation with the coefficients inside of it represented by the double integral, and then we're going to derive the 3D heat equation in much of the same way, and I'll leave that to you. I'll show what the 3D equation looks like, and I'll leave the actual derivation to you. Again, the third spatial directions, the same kind of ODE, you derive the coefficient in the same sort of way. Just to clarify again, multiplying the coefficients, applying orthogonality by integral to any term that involves the same variable that the term applies to. So if the integral applies to x, to y, to z, we're applying that. And so in a three-dimensional heat equation, we should wind up with three integrals for the coefficient. It should be a triple Fourier series, three series terms, a coupling equation involving three different values, and we should end up with a constant. And before we go on to the three-dimensional series, and before we show the solution to the two-dimensional series, I just want to talk about, coming up, we are going to look at what three-dimensional functions look like, because this is going to be a little confusing. So before we do that, let's talk about the two-dimensional function. Let's talk about the solution that we achieved, and we're going to talk about what that solution really means, how we represent it. So let's look at that now. Righto, so here's our solution in 2 dimensions, okay? And you'll notice the coupling equation, the Fourier coefficients that are included, all that. We already talked about that. But I want to talk about actually the form that this solution is going to present itself in, because this confuses a lot of people. So when people see a function of x and y, they assume that they're going to represent the function xy as z, right? Because think about it. In one dimension, we had y equals x, and then y we represented in the y dimension. And in the second dimension, we had function xy is equal to x and y, so we assume that we represented in the z direction. Now this is why, going back to the beginning, I represented the function as a function of a variable, not as y, okay? Because I don't want to confuse people here. I want to make this abundantly clear. We only represent that function as a direction because it's convenient to us. After the second direction, it doesn't become convenient, because we can have some plane xy, and we can have some heat, all right? But the thing is, the heat can be represented with another direction, but it can also be represented with something else. It can be represented with a constant. And this is going to be important when we go into the 3D equation, because think about this. When we have the 3D equation, when we have x, y, and z, what's the other direction? It doesn't exist. We can't do that. And it's not a vector valued function. We're not getting some vector at the end. What we're getting is a constant. Remember? I said that earlier in the video. We're getting a constant, and the constant is our temperature gradient. We call it our temperature gradient because really what we're trying to find is the change in temperature. We're not trying to find the slope of a line. Keep in mind that that has nothing to do with the geometry. Like I said, it's the boundary conditions that dictate the geometry. The boundary is the only thing that has to do with the geometry. When you work in 1D, even if you have a 2D curve, the equation is still going to be in 1D when you have a 2D plane. Even if there's some kind of graph that is in the z direction, again, you're only working with a 2D object. The most you can have is a plane. You cannot have anything in 3 dimensions. So when you get to 3 dimension, again, it's the boundary conditions that dictate the object. But now, what we're actually getting, we're getting a constant at each point. And think back to your Calc 3 class. Think back to your vector valued functions. See, normally, when you would do something in 3 dimensions, you would be taking a vector. You would be saying, like, okay, there's this directional vector. Each one of these variables in the x, y, and z direction has a certain bearing on the vector. And now we get a vector at each point, and that vector is going to influence our equation. But this equation is not fluidized. This equation is based on temperature gradient, right? It's based on diffusion. The diffusion equation is essentially based off of the heat equation, and vice versa, or if that makes sense, meaning that the heat equation is just a type of diffusion equation. So the thing here to keep in mind is that what we're really doing, the intuition behind this, is that we are trying to find the change in relative points in 3 directions, okay? So you're finding the change between the constants, okay? You're finding the infinitesimal change in the dx, dy, and dz direction between numbers. There's no vector value, there's no directional value, because, I mean, I suppose you could represent the directional value with a vector, but you would just wind up with your constant, and you wouldn't wind up with a particular direction. The constant wouldn't be a force. It would be a representation of temperature. There's no directional force, so we don't represent it with a vector, we represent it with a constant now. So the constant that we've ascertained is going to be the temperature, and what we're going to end up doing is we're going to end up representing it with color. All right, so now I'm going to put in a graph. Well, the first thing I'm going to do, I'm going to put in the 3-dimensional heat equation. I'm going to show you what that looks like, and again, you can ascertain this yourself with just the regular heat equation. And then I'm going to put in a demonstration, not a graph per se, but I'm going to put in how you would visualize a 3-dimensional surface with temperature at each point. Okay, just in case it wasn't clear. So I'll show people what our graph is going to end up looking like, sort of. Alright, so pay no mind to the practice problems right now. We're going to talk about those in a minute. Let's look at the 3-dimensional solution to the heat equation here, okay? We've written this out. This is nothing new. You can ascertain the solution using all of the techniques previously discussed, okay? So now what we're going to do is we're going to talk about how do we visualize this solution. Take a cube in 3 dimensions. Now remember, in 1 dimension, we had 2 points. In 2 dimensions, we had lines that denoted side lengths, and our common shape was a plane. Alright, so now in 3 dimensions, our common shape, our easiest shape in Cartesian coordinates, is going to be nothing other than a cube. Okay, take this cube here, this animation that I've put in. Watch how the animation moves. You'll see that at each point, the point is represented by a color. We've picked an arbitrary distance between each point, and in reality, this would be continuous. But we've broken it into points to show the idea behind this. At each point, we're finding a constant. Okay, and because that constant doesn't necessarily need to be a direction, we've proven in 1D and 2D, we could represent it with color, we don't need to represent it with direction. In 3D, the solution works now. So in 3D, what we're going to end up doing, we're going to end up getting our final function, and then we're going to graph the temperature gradient at each point. What we're going to do is we're going to base our density and our color off of the number achieved, okay? And so I'm going to show that in a computer program in a minute. But right now, just take in mind, look at this cube. Look at each point. Look how the temperature is denoted with a color. So keep in mind, we could do this in 2D, we could do this in 1D, but this is 3D now, and it's convenient for us to do this in 3D. In 1D and 2D, we like to use another direction to represent the temperature. It's okay, we can do that. But in 3D, there is no other direction, so just look at the colors for now. Okay, so initially I had 3 examples in this video that I was going to talk about. I was going to talk about 3 different questions, but because of the length of the video, I'm only going to talk about 1. So we're going to look at solving a very basic 3-dimensional heat equation problem here. Alright, so first, let's write out the equation we talked about in the video, okay? So we're going to say W of x, y, z, and time is going to be equal to something here. We're going to have 3 series. We're going to have infinity on the top of each. I'll fill in the bottom in just a second. Alright, so on the outermost we're going to have h equals 1. Middle we're going to have m equals 1. And then we're going to have n equals 1. These are all just arbitrary. So I'm going to write this a little bit differently than what we went over in the video. In the video we talked about having 1 over L, 1 over D, 1 over H, because we were going from length to negative length, but because we're going from 0 to length, when you think about it, initially when we solved that integral, we pulled out a 2 to the front, so we got 2 over 4, 1/2, and then 2L, so we got 1 over L on the front. If we never pulled out that 2, if we had 0 to L, so half the distance, we would have had 1/4 on the front, and we would have pulled 2L to the front, and then 0 would have just been 0, so we would have actually had 1 over 2L, or just L over 2. So our actual coefficient on the front would be 2 over L, and it's going to be 2 for all of these. So I'm gonna keep them separate to keep this simple, but I'm going to start with 2 over L times 2 over, let's see, D, times 2 over H. Okay. And so now we have, oh, and I'll bracket this just to make this more clear. Okay, so now we're going to have our triple integral here, and we're going to say, I'm just going to draw this in real quick, the 3 integrals. We're going to say on the tops here, we're going to have our respective, we're going to have H, D, and L. These are our lengths in each direction, so you can think of it as length, width, and height. We're going to have 0, 0, 0, okay? And then in here, we're going to have our function, our actual function of x, y, z. Okay. So now we're going to multiply this by our Fourier coefficients here, or what we talked about earlier. I guess this entire thing is the Fourier coefficient, but you know what I mean, multiplying by the sinusoids. So the first one, it doesn't really matter exactly what order we're putting them in, but we're going to put them in the order of integration just to make this simpler. So we're going to have h pi z over height here. Okay, then we're going to have sine of, let's see, m pi, I think this is y, yeah, y, over d, should be d, and then we're going to have sine, let's see, n pi x over L. Okay, so now that we have these, we're just going to say, on the first one, we're going to bracket it dz, dy, dx. Luckily, because there aren't any crossing over terms here, we can pretty much just treat all the outside as a constant. We can solve each dz, dy, dx individually. There's not really, again, it's just multiplying by some constant on the z term. So the z term is the closest in, it's 0 to h, and then you have the function times the sinusoid of the h term. So we can really just treat all this on the outside as a constant. There's the second part of the equation here. Obviously, this isn't the whole equation, so I'm going to bracket this. The second part of the equation, we're going to multiply by the sinusoids that we derived earlier, and the e term with the negative alpha t multiplied by the eigenvectors. But right now, we're just going to keep it like this, because the most important thing, we're going to solve this right now. So we're going to come up with an arbitrary equation here. All right. So if we come up with an equation here, let's just come up with a practice problem that makes sense involving these Fourier coefficients. So let's find the f of x, y, and z, and I'll just do a little sketch of what this looks like. I'll make something up, make up a period. So let's just say our f of x, y, z. Let's say that that's going to be equal to let's see here, negative x plus 2 cubed times x cubed, and then we're going to say that's all multiplied by negative y plus 2 cubed y cubed times negative z plus 2 cubed z cubed. All right, so that's going to be our function, and we're going to say that we're just going to give like some simple, these are kind of pseudo Dirichlet conditions. Let's say we have okay, let's say whoa, my marker's dying. Okay, f of x, y, and let's say 0 is equal to 0, f of x, y, and h, and in this case we're going to call h2 equals 0. Then we're going to have f of x, 0, z, that is a z, not a 2, we're going to say is equal to 0, f of x, 2, and z equals 0. And you can see the pattern here, so we're just going to finish this out. F of 0y, z equals 0, and f of 2y, z equals 0. I made this symmetrical for simplicity. It doesn't need to be symmetrical as long as the boundary conditions are homogeneous. But this is a pretty simple one to solve. Relatively simple. This is actually a pretty complex one to solve. But we're just looking at this inner integral right now, this Fourier coefficient. So let's look at like what a graph of this would look like, just to give you some intuition, like what I was talking about earlier. So let's say we have our axis here. Let's say we have our axis here, and I'm just going to represent this with a little arrow pointing inward. Okay, so this is our y, this is our z, this is our x. All right. Let's call this 2L. Let's call this backwards. Let's call this 2D. Let's go up. And let's call this right here, let's call this 2H. Alright, cool. So now we have like a cube. Okay, and remember there's a constant at each point, so I'm just going to draw sort of what this would look like. The exact middle should come out to be 1, and then we should have something that sort of looks like a circle, and then it's going to gradually start taking the shape more of the boundaries. And you can test this for yourself if you don't believe this, but this is what this should look like. Okay, and you could color the inside to represent this, but the inside here should be 1, and the outside here should all be 0. So 0, 0, 0, 0, and these are faces, not necessarily lines, but I'm just saying 0 on all the outside faces. So the exact middle is 1, the outside 0. It's all uniform. So this is a pretty simple problem on the surface to conceptualize. Pretty easy to solve. So let's actually start solving it. Okay, so let's look at the first integral we're going to want to do. Because our first integral is going to be from, let's say 0 to h, and again, we can pull out the 2 over h, 2 over d, and 2 over l terms. We can pull those all out on the front. So really, we're just looking at the integral here of 0 to h, and we're going to say, let's say f of x, y, and z times our relative sinusoids. And I'm going to save some paper. You can check and make sure this is true, but because these are all multiplying, they're not adding, they're all just multiplying, and because we can basically change the order of multiplication at will, and they're all going to multiply out to have their respective elements in them, we're just going to say our first integral, because in a triple integral we treat everything that's not part of the integral as a constant, and we can factor out the constant to the front. We're essentially just going to say our integral here, starting with z, because it's 0 to h, we're going to say here it's going to be negative z plus 2 cubed z cubed, and then we're going to say sine h pi z over 2, okay, dz. Alright, so this is our first integral. We pulled our constant out to the front. Our constant's every other term. So we're going to solve these one at a time, and then on the end we're going to multiply by our 2 over h, 2 over d, 2 over l, because again we just pulled those out anyway. So we're going to do this triple integral first. So right now we're just going to look at this integral. You might think this integral is going to be simple, but it's actually not. This is a really complicated integral. Not, I shouldn't say that. It's not complicated. It's just really long. So it's like, you know, they'd probably give you this on like an MIT integration bee and be like, solve it in 3 minutes. But no, this is actually just a really long repeating integration by parts integral. But that in mind, it is really long, so we're going to use up a lot of paper doing this. Right, okay, so let's get into it. First thing you're going to want to do, you're going to want a lot about 2 sheets of paper for this problem if you're doing it by hand, okay? So the first thing that I'm going to do is I'm going to apply linearity to the integral. Alright, so sorry if I'm writing small, but this is going to get really long. We're going to use multiple sheets of paper, alright? So the first thing... marker's not working. Sorry about that. Okay, so the first thing we're going to do, we're going to pull out this -1. We're going to get z minus 2 cubed, z cubed, sine of h pi z over 2. Okay, and some people get confused with these kind of integrals. We're treating the h like it's a constant, because it sort of is. So why do we pull out that -1? This may seem a little confusing. People may think, okay, well, like if you're multiplying by -1 on the front, you know, shouldn't everything flip sign? Well, not really, because we're only pulling the -1 out of this. When you think about this, this cube is actually, it's z minus 2 times z minus 2 times z minus 2. So when you pull out this -1 on the front, you're only impacting this term initially because this term can be factored in. So that's what we're doing. We're not multiplying by -1 on the front of the entire thing. So now we have our integral. This is what we want to integrate. We want the -1 out front like it's a constant. We want to pull out constants each time because we're going to be doing integration by parts and it just makes it neater. That's called applying linearity. So, okay, let's talk about what we're going to be doing now. So we're going to have integration by parts. Okay, so we're going to have u multiplied by the derivative of v equals u times v minus the integral of u, the derivative of u, times v. Okay, so that's our formula here. Alright, so let's start allotting things. We're going to have u equals, let's see here. We're going to have u equals z minus 2 cubed, z cubed. Okay, so that's our u value. U prime, we're going to save that for later. Let's say v, save that for a minute. Let's say v prime is equal to sine h pi z over 2. Okay, so now our v, we're just going to do a simple u substitution. I'm not going to write this out on paper because this is pretty intuitive. The thing on the inside, the u per se, is going to be h pi z over 2, and again, that's really just h pi over 2 is just one constant, z is the only variable, so we're going to wind up with the inverse of that constant out front, just like on a regular u sub. So we're going to wind up with 2 over h pi multiplied by, and again, the integral of sine is negative cosine. And you'll see why it's important to apply linearity in a little bit, because this is going to come back. This negative cosine in the integration by parts series that we're going to do is going to oscillate between negative cosine and positive sine when we apply linearity. Okay, let's talk about the u prime. I'm doing this with colors so you can sort of see more easily what's going on. So the u prime here, because we're working with the derivative of two things multiplying together, we're going to use the product rule. So we're going to say u prime is equal to, let's call it a prime b plus ab prime. Okay, so that's the product rule. So we're going to say that the actual u value here is equal to, again, this is just basic, you know, differentiation. You should have done this in Calc 1. So when I write out the u, I'm just going to write what a and b are. So we're going to have z minus 2 cubed, z cubed. This is going to go kind of fast because, again, you should know this from Calc 1, and this is a long integral, so I don't have time to talk about it all. So from here on out, this is going to go pretty fast, okay? So we're going to say that u prime here is equal to 3 z minus 2 squared z cubed plus 3 z minus 2 cubed z squared. Okay. And so the 3, again, the 3 is just coming from in front of the z term, and we've pulled it out to the front. So now that we have this, we're going to reform our entire integral here. So we are going to end up getting negative 2, whoa, pen's starting to go, negative 2, and this is from the cosine, so it's this 2 here and the negative on the front. So we're going to get negative 2 multiplied by z minus 2 cubed z cubed times cosine h pi z over 2, and this is all going to be over h pi, and you're going to want to keep it that way. You're not going to want to distribute the negative 2, you just want to keep it all in this form yet. We're going to be subtracting now, and again, this is our v times our u term. Alright, so that's what we got here. So now we're subtracting. Now we have an integral. Oh look, it's another integration by parts. So this is going to go on for a while. Before I write this integral, I'm just making that clear. This integral will eventually terminate, but right now it's just one huge integration by parts. So, okay, let's look at this integral here. So initially, we're going to have, there's a negative on the front because we're subtracting here in our formula. So we have a negative on the front here. Okay, so now we have the integral negative, I'm going to pull the negative 2 to the front from the cosine term, so I'm going to have negative 2 multiplied by, we're going to call it, why did I do that? Sorry. We're going to call it 3z minus 2 squared z cubed plus 3z minus 2 cubed z squared, that's what we got earlier, times cosine, times cosine h pi z over 2, and then this is all going to be over h pi. Alright, so now we have this integral here, and we are gonna apply linearity, because it's gonna become relevant in our next integral. So when we apply linearity, this negative 2 distributes, both of these are 3's, so there's going to be a negative 6 on the front of each of these. So we can actually end up rewriting this integral. We can end up rewriting it as the integral here, let's say negative 6 times, let's see here, I'm going to write this as a double parenthesis, z minus 2 squared z cubed plus z minus 2 cubed z squared. Okay, and again, just the regular junk out front, h pi z over 2. And this is all going to be over h pi. It's still all over h pi. So when we apply linearity, we should be able to pull out this negative 6 over h pi. That's the biggest thing we can pull out in terms of our linearity. So here's what we're going to do. We're going to allot an entire second piece of paper here. So we're going to allot this entire second piece of paper here, and we're going to write incredibly small. Okay, so we're going to say negative 1, because that's what we pulled out initially, times the entire thing in here. Okay, so we're going to say negative 2 z minus 2 cubed z, let's see here, z cubed, sorry about that, cosine of h pi z over 2 all over h pi. Okay, and now we're going to say plus, because remember on our other problem we actually had a minus 6 6 over h pi. And we're subtracting the integral, so you know a negative times a negative is just a positive. So now we're going to have plus 6 over h pi. And again, now here we have our next integral that we're going to do. Okay, so now that we have our next integral that we're going to do here, we're going to be looking at sorry, just going to start on another piece of paper here. Okay, so now we're going to be looking at the integral here. Let's draw it out, next piece of paper. This is our next integral. And we've already pulled the 6h pi out front. So we're going to be looking at the integral here of z minus 2 squared z cubed plus z minus 2. Got to be careful to draw these 2's in so they don't look like z's. And then this is all going to be multiplied by cosine h pi z over 2 every single time. Okay, and so again, we pulled out the h pi on the bottom, so this is our new integral now. All right, and just for clarity, I like to write this out every single time. You don't necessarily have to do this, but I love writing out this u v prime equals uv minus the integral u prime v. Okay, I love doing that because you'll get confused really easily because this goes on for a while. All right, we're going to be going through a couple sheets of paper, like more than a couple. We're going to be going through a lot. So this goes on for a while, so you might want to write this out each time, might want to use different colors. All right, so again, we're going to say u is equal to z minus 2 squared z cubed plus z minus 2 cubed z squared. Okay, so that's all u prime. We'll get to that. V prime, oh, why did I do that? Sorry, just v, and let's say v prime is cosine h pi z over 2. Again, v is just going to become, again, we pull out, it's going to be 2 over h pi. You'll get that every time. This term repeats, so you'll quickly realize when we apply our linearity, this is going to oscillate from a negative cosine to a positive sign with the same coefficient out on the front each time. H pi z over 2. Okay, so our u prime here, going to pick up the pace a little bit. Now we're going to say we have two terms adding here, so we're going to say u prime equals, well, let's just first say u equals a b plus c d. Okay, so u prime is going to be a prime b plus a b prime plus, let's say, c prime d plus c d prime. Okay, so let's talk about the first one. Let's just talk about the a prime b, a b prime. So that first one is going to come out to be 2z minus 2z cubed plus z minus 2 squared 3z cubed. And you can pull the 3 out to the front if you want. So that's going to be our first one, so I'm just going to bracket that real quick here. And again, you can check the math on this. 2 times z minus 2. If we go back and look here, that's just this, the derivative, z cubed plus, again, you can just go through and check all this. So you know what I'm doing, but this whole part here is this right up here. So now we're going to do the next part here. And again, I'm just going to bracket it. This is going to start moving quicker. This is a really long integral. Okay, we're going to get 3z minus 2 squared z squared plus z minus 2 cubed 2z. Alright, so now we have that entire thing. So we're going to simplify here. We're going to get 6z minus 2 squared z squared plus 2z minus 2z cubed plus 2z minus 2 cubed. Nice how it's always z minus 2z. Okay, so we simplified that. Again, we combined the two terms with 3 in the innermost. So now we're going to wind up with our final integral here. We're going to get 2 z minus 2 squared z cubed plus z minus 2 cubed z squared, all times sine h pi z over 2 all over h pi. We're going to be subtracting now. I'm going to move on to the next line just to save space. We're going to be subtracting the integral here of, just save space, I'm going to say u prime multiplied by 2 sine h pi z over 2 all over h pi. So we're going to write this on the next page, but again, let's go back to our initial sheet here. This is important, so let's go back to our initial sheet here, fill it in. Organization is key in these problems. So now we're going to get multiplied on the inside 2 z minus 2 squared z cubed plus z minus 2 cubed z squared, all times sine h pi z over 2, and then this is all going to be over h pi again. And now we're subtracting. So looking at our next term and going back to this right here, we're going to say that within this, we're going to be able to, when we multiply, we're going to be multiplying here by 2 on the front of u prime. So when we multiply by 2, the 6 will become 12, the 2 will become 4, and the 2 will become 4. So we're going to divide out 4. Can't do anything about the 12. It's going to become 3 times this term. The others are just going to be these terms. So let's say on here, we're going to divide out, we're going to divide out, we're going to get minus, and we're dividing out, this is positive, and there's a minus, so it's going to be negative 4 over h pi. Moving on here to our next bracketed thing, and going back to, now we are on to our third sheet of paper. Going back here, we are going to get, I will just write the integral here to clarify, 4 over h pi, because we represented it with u on the other page. So we're going to get 4 over h pi. We're going to get multiplied by 3 z minus 2 squared z squared plus z minus 2 z cubed plus z minus 2 cubed z, and then this is all times sine h pi z over 2. Okay, so this whole thing repeats. I can tack on the negative here just because we're subtracting it. That was what we got on our sheet of paper over here. Again, it's negative, and we're multiplying on the front here. But again, we're not worrying about this right now, so we're just going to cross that out. We don't care about that. We just care about the integral. So when we do this integral, you might be thinking, why do you just keep doing integration by parts over and over? Like, isn't there an easier way? I'm not sure if there is an easier way. I'm not an expert on integrals. I don't think that there's a substitution in here that works conceivably. I like to think I'm a pretty smart guy, so I would like to think that I would have figured it out by now. I don't think there's any substitution that works. This does eventually terminate. You can tell because the great thing about integration by parts is when you keep taking the derivative of something with a high enough power, it's going to keep going down and down in power, even if it's multiplying like this, like factors. So eventually we will get it to be a low enough power that we can do a substitution. The powers are going down slowly. It's hard to see a pattern right now, but integration by parts on something like this will terminate eventually, and I think it's the easiest way. If you have an easier way, please tell me in the comments. Again, this is going to go on for a couple sheets, so we're going to try and move a little bit faster after this. Okay, so again, we're just going to write this out. U times v prime equals uv minus the integral of u prime v. Okay, so we're just going to mark down u, v, u prime, and v prime. Okay, so u prime is going to be sine h pi z over 2. We already know here it's going to be 2 over h pi times negative cosine h pi z over 2. That's just going to oscillate the entire time. Okay, so u, this is a longer one. U is going to be, 3 z minus 2 squared, z squared plus z minus 2z cubed. I gotta write smaller. Plus z minus 2 cubed z. Okay. Shoot. Sorry about that. Wrote the wrong areas there. U prime goes up here. Sorry. This is v prime, and then this is v. My bad about that. Okay, so now u prime, we're going to solve for u prime. We're going to say u prime equals, not going to do that yet. First of all, let's establish u equals a, b plus c, d plus e, f. Okay, we have 3 terms here. Alright, so we're going to say first a, b. We're going to get 6 z minus 2 times z squared plus 6 z minus 2 squared z. Alright, now for CD, we're going to get z cubed plus z minus 2 3z squared. Okay, and then finally for EF, we're going to get 3z minus 2 squared plus, times z on the end there, my bad, plus z minus 2 squared. Okay, so we're going to add those all together real quick. We're going to get 6 z minus 2 z squared plus 6 z minus 2 z minus 2 squared, sorry about that, z plus z cubed plus z minus 2 3z squared plus 3 z minus 2 squared z plus z minus 2 cubed. Long integral. So we're going to simplify that. It can be simplified. So we're going to end up getting 9 z minus 2 z squared plus 9 z minus 2 squared z plus z cubed plus z minus 2 cubed. Alright, so moving on to our next sheet of paper here, still on the same integral. Okay. Okay, so moving on to the same integral, we're going to plug everything back in. We're going to end up getting, for the front part, we're going to get negative 2, 3 z minus 2 squared, z squared plus z minus 2 z cubed plus z minus 2 cubed z, and all this is going to be multiplied by cosine h pi z over 2. Remember the negative 2 on the front we simply pulled out. This is all going to be over h pi. Okay, then we're subtracting our integral here of, again, we're going to say u prime for simplicity, times negative 2 cosine h pi z over 2 all over h pi. Okay, so that integral is done for now. Okay, so now we're going to move back to our original sheet here, which we worked on earlier. Again, important to keep organized. So here we're going to be plugging in. We had, let's see, negative 2, 3z minus 2 squared, z squared, plus z minus 2z cubed, plus z minus 2 cubed, z cosine h pi z over 2 all over h pi as always. And now I'm gonna call this minus because we're gonna pull something out. We can make it a plus if that pulled out constant happens to be negative, because negative times negative is a positive. So now moving on to the next integral. Right, so normally I would just get a new page to start the integral, but let's just continue it on this page to save paper. So don't be confused. We're going to go back to solving our new integral in a minute, but let's just pull out the constant here. Alright, so this is equal to, again, let's call it minus, because that's what we were doing on the other page, minus negative 2, 9z minus 2 squared z plus 9z minus 2z squared plus z cubed plus z minus 2 cubed, all times cosine h pi z over 2 all over h pi. Okay, so when we pull out our constants to the front, unfortunately, because we have z cubed here and there's nothing in front of it, the most we can pull out is actually the negative 2. So we're going to get positive 2 over h pi on the front. The integral here, 9z minus 2 squared z plus 9z minus 2z squared plus z cubed plus z minus 2 cubed, all times cosine h pi z over 2. Okay, let's move on to a new sheet of paper now. Okay, so now we wrote that all out. Let's have our integral here, u times v prime equals u v minus integral u prime v here. So u prime, maybe I should have written these farther apart, v prime equals. Okay, so u, again, let's just write this out again. We just did this, but 9 z minus 2 squared z plus 9 z minus 2 z squared plus z cubed plus z minus 2 cubed. Okay, we're not going to worry about u prime yet. So v prime was negative, whoops, why did I say negative? Just cosine h pi z over 2. This is going to oscillate. It's going to become sine h pi z over 2 multiplied by 2 over h pi. Remember the pattern. Okay. Long integral. Okay, so now moving on, you're going to have u prime here. Again, define u. We're going to say u equals, okay, ab plus CD plus, and we don't need to define these are just, there's no product rule here, z squared plus z minus 2 cubed. So let's just get this out of the way right now, because this is less important. So we're going to say that this is essentially going to be equal to, the derivative here is 3z squared plus 3z minus 2 cubed. Alright, so now let's worry about AB. So we're going to say AB is going to be 18 z minus 2z, and as you can see, the exponent's actually going down like I was talking about. 9 z minus 2 squared. Still a long process, so CD is 9z squared plus 9z minus 2 times 2z. Okay, so now we have this whole thing. Alright, so now we're going to get these all together. So what we're going to be left with is, we're going to be left with 36 z minus 2z plus 12 z minus 2 squared plus 12 z squared. Okay, so that's what we're going to be left with essentially. So now we're going to move on to our next step here. We're going to move on to putting this all back into the original equation. I don't know if I should start this on this sheet of paper. Alright, I'm going to start this on this sheet of paper, so I'm going to write our constant. We're going to plug it into our original equation, and then we're just going to write the integral on the next page. Okay, so now we're going to be left with, whoa, this pen's dying, 2 times 9 times z minus 2 squared, z plus 9 times z minus 2 z squared plus z cubed plus z minus 2 cubed, all multiplied by sine h pi z over 2 all over h pi. So we're going to leave that for now. Let's go back to our initial equation. So back here, this is our initial equation, and looks like I actually forgot a step here. So because we pulled out 2 over h pi initially back on this integral right here, we're going to plug that back in. So we're going to get plus 2 over h pi all multiplied here by 2, we're just plugging this back in, 9z minus 2 squared, z plus 9z minus 2z squared plus z cubed plus z minus 2 cubed, all times sine h pi z over 2, and then this is all going to be over h pi. Okay, and so again we're going to allot our subtraction here, going back to our integral. We're going to say new sheet of paper. Time for a new sheet of paper now. Okay. Because I said I'd write the integral on the next page. So really what it is here, it's minus the integral. We didn't write that part from our last integral. So minus the integral, this is the new integral. We're going to say minus 2 times, what was it again? 2 times 36 z minus 2z plus 12 z minus 2 squared plus 12z squared times sine h pi z over 2, and once again all over h pi. So what's the highest thing we can pull out here? This is a negative on the front. Everything here is positive. The highest thing we can pull out, multiplying by the negative, is 24 over h pi. Let's go back to our other sheet here. So we're going to say minus 24 over h pi. And we're going to have our bracket here. Okay. So minus 24 over h pi. Integral here. We don't care about this anymore. Okay. So now our integral is going to become 3z minus 2z plus z minus 2 squared plus z squared. So this is simplifying, times sine h pi z over 2. Okay, so now that this is simplifying, we're going to start with our next integral. Once again, we're going to write it out. We're going to have the integration by parts here. U times v prime equals uv minus the integral u prime v. Okay, so once again, u, I'm going to move this over this time, u prime v and v prime. Once again, our v series is just going to be sine h pi z over 2. So we get the oscillating term again. We're going to get 2 over h pi times negative cosine h pi z over 2. Okay, u is just going to be 3 z minus 2 z plus z minus 2 squared plus z squared. Sorry about that. So u prime, let's figure it out. Again, we're just gonna write u prime equals u equals, let's define u. So we're gonna say u is ab plus z minus 2 squared plus z squared. So again, this region doesn't require a product rule. We're going to say that it simply is 2z minus 2 plus 2z. Alright, so now for the AB region, we're going to say it's 3z plus 3z minus 2. Okay, so now when we simplify all this, we're going to end up with 5z plus 5z minus 2. Okay, so now if we plug back into our original integral here, we are going to end up getting this very long first part, which I'm going to write on this page. It's going to be negative 2 3z minus 2z plus z minus 2 squared plus z squared cosine h pi z over 2 all over h pi. Fortunately, we gotta write this entire thing again on our other sheet of paper. Again, organization is key. Said that about 4 times in this entire presentation. Alright, minus 2 3z minus 2z plus z minus 2 squared plus z squared times cosine h pi z over 2 all over h pi, and again have our subtraction. Let's go back to our integral though. So now we're going to start on a new sheet of paper now, starting with a new integral. So this is our new sheet of paper here. Alright, so now we're going to, let's see if we can get this done on one sheet of paper. We're going to have our integral here. It's going to be the integral, it's going to be the negative integral of negative 2 multiplied by 5z plus 5 times z minus 2 cosine h pi z over 2 all over h pi. Alright, so let's look at the biggest thing we can factor out right here. And we're going to say the biggest thing we can factor out right here is going to be negative 10 over h pi. So that's just going to become negative times the negative 10 over h pi times the integral here of z plus z minus 2 and all times cosine h pi z over 2. Alright, so let's go back to our other formula sheet once again. Plus 10 over h pi bracket. Okay. Back to our integration step here. So now that we have this integration step here, it's important to recognize we can actually factor out something else. So when we have our integral here, we're going to have z plus z minus 2 cosine of h pi z over 2. We can actually factor something else out here. So we can actually factor out the 2. So we're actually going to wind up with 2 multiplied by the integral of z minus 1 cosine of h pi z over 2. And this should start to be looking like a substitution problem. We still have one more integration by parts to do, but this should definitely be starting to look like something you can do a substitution with. So going back to our initial paper here, we're going to write this in. We're going to bracket this. We're going to say 2. Alright, let's go back. So we got one more integration by parts to go. So we're going to say 2 times the integral here u v prime equals, we're going to say 2 times uv minus the integral here u prime times v. Alright, so we're mostly focused on this right here. This could get a little confusing, but don't worry, it'll all come back together. U equals z minus 1. We're going to say u prime. We don't have to do anything this time. This is just 1. U prime's just 1. How great. Okay, v and v prime. We know v prime is cosine h pi z over 2. V is just going to be that repeating series, sine h pi z over 2 times 2 over h pi. Okay, so now we're going to put this all back together. We're going to get 2 z minus 1 sine h pi z over 2 all over h pi. Okay, and minus the integral here of 2 over h pi times sine h pi z over 2. This should definitely look like a sub-problem to you at this point. Let's go back to our initial equation here. Let's see if I can't write it in small enough. So we're going to say 2 z minus 1 sine h pi z over 2 all over h pi. Okay, and then we're going to be adding, well, let's call it subtracting right here. Let's just say we're subtracting till we're ready. So now now we're going to have the integral here. I'm writing this in green because it's a sub problem. 2 over h. Why did I write h up there? 2 over h pi times sine h pi z over 2. All right, so we're just gonna do a simple u sub here. We're gonna say u is equal to h pi z over 2. We're gonna say du is equal to h pi over 2, because when you think about it, this entire thing is just a constant. Z's multiplying it. So we're just going to say dx, because again, there technically is a dx here, so we're just going to do some basic algebra. We're going to say dx is equal to 2 over h pi du. Alright, and so since we technically have a dx here, because this entire thing is the integral, we're going to say that because dx is equal to this, we're going to turn this entire integral into, we're going to pull the constant out front. We're going to say 4 over h squared pi squared, and then the integral is just going to be sine h pi z over 2. And if you want, you can just, it doesn't matter right now, we're going to say du, so we can actually just keep this in the form of u. Let's just do that for now. Let's just keep it in the form of u to be accurate, to be precise. So it's really just sine of u right now. And we pulled this entire constant outside, so when we integrate sine of u, it's just going to become negative cosine of h pi z over 2. Plug that back in, like again, it didn't really matter, but okay, here we go. And we're multiplying this entire thing by 4 over h squared pi squared. Alright, so we've solved our integral now. Let's just plug everything back in, just to be consistent. Alright, so now we're going to plug this back in. So it is a plus 4 over h squared pi squared times cosine h squared z, oh, what is it? H pi over z over 2. We're going to bracket this. Let's see how many times. 1, 2, 3, 4, 5, 6, 7. Alright, so now it's bracketed. So now we have our entire integral, so that's good. So our entire integral has been solved here. Oh, just to clarify in case it wasn't clear, because we were subtracting earlier and this was originally negative 2 over h pi and we multiplied, it was negative 4 over h squared pi squared, and that's how we got the plus, because there was a negative times a negative. Sorry about that. So now we have our entire integral here, but this isn't very neat. So we're going to work on simplifying now, because that was a really long integration by parts, and there's no way that we're going to solve this. Thankfully, the equation is symmetrical, the equation we're working with. So, you know, when we do the triple integral, we should get the same result each time. So when we simplify this, we should be able to plug in our limits of integration and just get something in terms of constants and h. So it should be like a series, and then we're going to multiply by our sinusoids. But right now, we want to simplify this. Right, so now that we have the solution, I took the time to just write this out. This is the simplified version of the solution. I hope you don't mind I didn't show all these steps because it's just a pretty long process. We went from essentially having this right here, and we've just multiplied by all the coefficients. So within all these brackets, we've you know, taken all these coefficients and turned that equation into this. It's a little bit shorter, a little bit neater, and it's all plus or minus. There's no multiplying except for in the individual terms. So all the denominators, the terms within their respective denominators multiply, but all the dissimilar denominators just add or subtract. So this makes the integral a lot easier when we plug in the bounds of integration. Right, so here's just a quick graph so you can see what's going on. You can see how the integral correctly maps the equation that we had. And I haven't done anything with the end term yet because this is a Fourier series. It's different than the integral, so we were just specifically looking to make sure we did the integral correctly right now, so I just set the end term to 1. So now let's talk about the actual Fourier series. Right, so we could go about this the brute force way, but let's just use our intuition real quick so we don't have to do that. So we know in a Fourier series, we know based on our limits of integration and just what we've talked about, the heat equation in general, we know that when we have cosine of 2 over 2, with this n pi term, you're gonna get an oscillating -1, +1, -1, +1 based on the n value. So when we plug in that limit, cosine is just going to be -1 to the nth power. All right. So let's look at what else we know. We know that the terms that are relevant are the terms that have something like this, where z is by itself. Because if we plug in 2 here, we're going to get, 2 minus 2 is 0. We're multiplying, that whole thing cancels. But let's just say we plug in 0 here. We're multiplying by that, so that turns into 0. So we really need things that are by themselves. Again, if we plug in 0 here, it doesn't even work. So really, for 0 and for 2, we're only looking at cosine terms first of all. We can't look at sine terms. And further than that, we're really going to only be interested in this h pi to the 5th and this h pi to the 7th, these two terms, with both the 0 and the 2. Because actually, they're the only ones where you can plug in 0 or 2 and have it still be something. So, like, let's say you were to plug in 0 here. This is the only one where there isn't a z coefficient on the front, so not everything in this box cancels to be 0, so it'll actually be 4 in here. So we're really only interested in these two terms right here. Those are the only terms we care about right now. Okay, so let's just write out what a Fourier series would look like here. Alright, okay, we're concerned with these two terms, so let's start first of all, let's start with, plugging in, well, we could start with 0 or we could start with 2, so what makes more sense? I'm thinking we're going to start with 2. Like in a regular integration problem. So I'm gonna say, all right, let's start with 2. Let's start with the first term, right? So we're gonna say 2, 3, 0, 4. All right, we're gonna multiply within this bracket. Okay, so we know z squared if we're plugging in 2. We know that's gonna be 4. But everything else in here is gonna be 0, right? So we just get this times 4, and now we get times cosine of h pi, and then z is 2 over 2. But we already know what that is, so we don't need that. We need -1 to the nth power, right? And this is all going to be over h pi to the 5th, right? So now that we have that, we're going to look at the second one in here. And again, you want to be careful. The second one, you're actually subtracting. So you want to make that clear. And I'll bracket the whole thing here. So the second one, you're subtracting. All right. So in the second one, we're going to have 9, 2, 1, 6, 0. Don't be intimidated by the large numbers. And then it's going to be multiplied by, again, we said this is -1 to the nth over h. Why do I keep saying to the nth? I'm sorry, to the hth. Sorry about that. H pi to the 7th. I'm used to saying n in a series. Sorry about that. I'm used to treating that as a series term. Okay, so now we finish this up. We know what both of these are. Okay, and now we're going to add, okay, for 0. So for 0 here, we're going to do the same thing. We're going to say 2, 3, 0, 4. Alright, and on the inside, z squared, if that's 0, that's going to be 0, plus 3, 0 minus 2 times 0 is just 0. So we're really only looking at the final term, which is -2 squared. When you think about it, 0 minus 2 is just -2 squared, so that's 4. And you'll notice this is looking similar. So now we're going to have multiplied by, we know that cosine, when we multiply by 0, the cosine term doesn't oscillate from positive to negative. It's just going to be times -1. And this is all going to be over h pi to the 5th. And then we're going to subtract, and I guess you could change this to be adding if you pull out the -1, but let's just leave it like this for simplicity. Okay, we're going to subtract 92160, and again, this cosine is just going to be -1, and that's what I was saying you could pull out, but let's just leave it like this, h pi to the 7th. Okay, so now we have this thing here, alright, and really what we would do is we would put the series term on the front. Now remember, I said you have a 2 over, what bound are we working with here? We're going to have a 2 over h on the front, but we know h is just 2, so that's just going to be 1. So this is our actual Fourier series, and this can be visualized because when you think about it, it doesn't really matter what dimension this is. This entire thing is symmetrical. So let's just visualize this using x and y. Let's just look at this in one dimension. Right, so as you can see here, by the changing images, our Fourier series does work. We found it at least for one dimension, alright? And as you can recall, by the triple Fourier series, because we can treat other terms like constants, we've basically solved for all the dimensions now, because this thing is symmetrical, and because the coefficients on the outside are just going to be 1, really, we're just going to combine terms now, so we can get our final equation. And here, I know it's a little hard to see, I made it in Desmos, but here I'm showing that you can multiply the sinusoid terms and the Fourier coefficients when they're symmetrical with different variables to essentially get the graph that we want. It's hard for me to do this in 3 dimensions. Possibly in the next heat equation video, I may use art of illusion to show diffusion in 3 dimensions. But right now, it's taking up a lot of my computer power, and this video has gone on long enough, so hopefully this will be enough proof for you that it works in 1 dimension, it works in 2 dimensions, and ergo, because we proved the solutions and the coefficients in the 1st dimension and 2nd dimension work in the 3rd dimension, hopefully you'll believe that the graphs that we render will also work in the 3rd dimension. So let's just write out our final response now, and then we'll essentially be done after we find the eigenvectors. Okay, let's put together our final solution here. Alright, so this is going to be a long one. We're going to have W of x, y, z, and t is all going to be equal to, alright, we're going to start with 3 series. They're all going to go to infinity. Alright. Our series again are going to be h equals 1, m equals 1, and n equals 1. Alright, so now we're going to have everything that we wrote before. So we're going to start on the inside with z. So we're going to have 2, 3, 0, 4 times 4 times -1 to the h over h pi to the 5th minus 92160 times -1 to the h all over h pi to the 7th. Alright, now we're going to get plus 2304 times 4 times -1 all over h pi to the 5th minus 92160 times -1 h, whoa, sorry, not h, absolutely not h, h pi 7, and now this entire thing is going to be multiplied by sine h pi
z over 2. And this was our first one-dimensional Fourier series we rendered in Desmos. This is what we got, essentially. So I'm sorry if that wasn't clear, but we need to include the sine term to get the complete Fourier series. Alright, so now let's go on to our y component. We're going to be multiplying here, so I'm going to add here times, and it's going to be the same thing. So 2304 times 4 times negative 1 to the m over m pi to the fifth minus 92160 times negative 1 to the m over m pi to the seventh plus 23044 negative 1 over m pi to the fifth minus 92160 times negative 1 all over m pi to the seventh sine m pi y over 2 times 23044 negative 1 to the nth over n pi to the fifth minus 92160 times negative 1 n over n pi to the seventh plus 23044 negative 1 n pi to the fifth minus 92160 times negative 1 over n pi to the seventh. And you can see why usually we use computers to do this kind of stuff. N pi x over 2. Okay, now this entire thing is going to be multiplied by e to the negative alpha. I never defined what alpha was, so it doesn't really matter. We're solving the equation, doesn't matter in the least. Times t multiplied by, here we're going to have n pi over, and let's see what L is. L is just 2, they're all 2, so that's squared. And I should really double bracket this, multiplied by t. And then we're going to say plus m pi over 2 squared plus h pi over 2 squared. Okay, so basically now we have the entire heat equation. This is the solution to our heat equation. So what this should look like, we should have a cube with our given dimensions. So we're going to say 2 outward, we're going to say 2 up, 2 and 2. Okay, so and then this is the origin, this is 0. So again, in the center we want the w value in the center, so we want to say w equals 1 for the central origin. And then for all the boundaries, we want to say that this entire thing is 0 on all the boundaries. So, and again, these are faces, not sides. I'm just trying to convey that. So again, the heat should look initially like this. So do a quick little sketch of it. And it should be changing. Again, we have negative E value. We know when the magnitude gets larger and larger and larger in negative E, that negative E is asymptotically approaching 0. So we know that this value is going to get smaller and smaller and smaller. So then we're going to have a cube, and these lines are going to essentially travel further inward on the heat map. So, you know, we're going to end up with, eventually, the cube is just going to be a cube. And this is due to Fourier's law. So the origin here, eventually, we're going to say, as the limit approaches infinity, we're going to say that W is going to equal approximately 0 at the center origin there. Okay? So that's what's happening. This is the equation that you would use in a computer program to model this happening. This is the solution to a problem in 3 dimensions. So that's what it would look like. Next video, we're going to be talking about polar coordinates. The video is essentially done. I've said everything that I wanted to say. I know that the video quality is bad. So, again, I don't really have the money for a good camera. The best thing you can do for me would be like and subscribe, share my stuff. So I'd really appreciate it if you like my video, you know, please show that by liking and subscribing. And if you didn't like the video, you know, leave a comment, tell me what I could do better. I understand the video quality is not very good, so if you know, say that, we get it. I gotta pay for college, I gotta do things like that. So, you know, not much I can do for now, but I hope that the video was educational and I hope you liked it. So, thanks for watching.